Hi everyone. In this video we're going to talk about the dimension of a subspace as well as define these fun words of rank and nullity. And then we'll loop this back and talk about how it corresponds to the invertible matrix theorem. Alright, so let's begin by talking about a definition. The dimension of a subspace, or a vector space if you're in a general vector space. The dimension of a subspace, and suppose that we have a non-zero subspace, because we'll see that there's a wrinkle if you have a subspace that's just the zero vector. But suppose we have a non-zero subspace. The dimension is the number of basis vectors in any basis for H. And our subspace is called H. So the dimension of a subspace H, which is non-zero, is the number of basis vectors for any basis of H. And it's a theorem to actually to show that any basis of a subspace has the same number of elements. So that's a thing that needs to be proven. But it is true, and we call that number the dimension. There is a fun wrinkle here. What about the dimension of the subspace that's just generated by the zero vector? Well, does the set of just the zero vector really have a basis? It's the only element's the zero vector itself, and we know that if the zero vector is in any set, it has it's not linearly dependent. So how could it be a basis, right? A basis has to be a linearly independent set that spans the space. And if the zero vector is in there, it can't be linearly independent. So that's kind of weird. But we say that the dimension of a zero subspace is zero. Yeah, this is our definition to keep things consistent. Let's do an example. What do you think is going to be the dimension of our favorite space Rn? Well, it's going to be n, right? Why? Because our basis, a basis for Rn, is the set E1, E2, all the way up to En, right? And how many vectors are in our favorite basis for Rn? There are n such vectors. Yeah? Let's do another example. What's the dimension of the span of the set of vectors 1, 2, 3, 4, 5, 6, -2, -1, 0? What's the span, or the dimension of the span of these three vectors? So remember, what's the dimension? It's the number of vectors in any basis. Yeah? So we know that these three vectors span this subspace. That's true. But what's a linearly independent set that also spans? Pause the video and see if you can figure this out for yourself. So to determine a set of vectors that's linearly independent and spans the space, let's take our three vectors and and row reduce. 1, 2, 3, 4, 5, 6, -2, -1, 0. Yeah? And now really what we want is a basis for the column space of this matrix. Yeah, I just took my vectors, put them in the columns of this matrix, and I really now want a basis for the column space. And how do we do that? We row reduce, and we pick off the corresponding column, or the columns corresponding to our pivot entries, right? So how do we row reduce this? Well, in the previous video, we saw that this has reduced row echelon form. This is by previous video. This is where I grabbed this example. We have the reduced row echelon form of 1, 0, 2, 0, 1, -1, 0, 0, 0. Yeah? So where are our pivot columns? The pivot columns are in the first and the second columns, right? So how many pivot columns do we have? We have two pivot columns. What is therefore a basis for this subspace, the span of these three vectors? A basis for this subspace is just the set of the first two column vectors, right? So 1, 2, 3, 4, 5, 6. Yeah? So this is a basis, and how many elements are in this basis? There are just 2. So we know, therefore, that the dimension of this subspace is 2. Yeah? Good. All right, so let's define a fun word. We know that the dimension of a column space is going to be important for us with our last example, and with that we have a nice definition. It actually has a nice name. The rank of A, and we're going to usually denote this as just rank A, or rank of A if you want to write it as a function, is the dimension of the column space of A. Yeah, it's the dimension of the column space of A. And so just to be clear, if we have the matrix A equals to 1, 2, 3, 4, 5, 6, negative 2, negative 1, 0, let me make sure that was the matrix. Yeah. If this is my matrix A, then the rank of A is equal to 2, because the dimension of its column space was 2. And how do we identify the rank of A? This is really important. Stars and happy faces, right? This is really important. How do we identify the rank of A? It was given by the number of pivot columns. It's given by the number of pivot columns in A. And remember, we identify the pivot columns by row reducing and just seeing which columns have the pivots. Yeah. But remember, if every column of A is either a pivot column, yeah, so it corresponds to a basic variable, or it corresponds to a free variable. And remember, what did we use the free variables for? That helped us get a basis for the null space, right? So that helps us with the following idea. The dimension of the null space of A is the number of free variables. Because every column in a matrix either corresponds to a basic variable, so it's a pivot, or it corresponds to a free variable. Yeah? And often you'll see that the dimension of the null space of A has a fun name called the nullity. The nullity of A is often what people refer to as the dimension of the null space of A. Okay? And remember what we said. We said that either any column of a matrix is either corresponding to a basic variable or a free variable. So what happens if you sum up the number of basic variables and the number of free variables? You better get the number of columns, right? So I'll say that one more time. If you sum up the number of basic variables and you sum the number of free variables, you have to get the number of columns. And this is called the Rank-Nullity theorem. The Rank-Nullity theorem says that if A is an m by n matrix, yeah? If A is an m by n matrix, how many columns do we have therefore? We have n columns, yeah? Then we have to have the following equality. We must have that the rank of A plus the dimension of the null space of A, or the nullity of A, right, is equal to n. And again, this needs a star because it's super, super nice. And you'll see lots of nice homework examples showing why this is such a powerful theorem. Yeah? All right, so let's talk about the invertible matrix theorem again. Now we're ready to talk about the invertible matrix theorem. And we know that we already have like 14 the following are equivalent. So what's 7 more, right? Let A be an n by n matrix. Because remember, if you're invertible, you have to be square. Then the following are equivalent. 1. A is invertible. 2. The columns of A form a basis for Rn. Why is this true? If we're invertible, remember that the columns must span Rn. Yeah? Well, if the columns span Rn, and if it's invertible, we also know that the columns are linearly independent, right? So if the columns of your matrix span Rn and they're linearly independent, then they must form a basis for Rn, right? Just combining those two properties gives us this new property of invertible matrices. 3. If the columns of A form a basis for Rn, then what do we know about the column space of A? That's Rn, right? This is just another way of saying that the columns span Rn, right? The columns span Rn. We can repackage this now and say that the column space of A is equal to Rn. 4. Well, if the column space of A is Rn, what's the dimension of the column space of A? It's n, right? Because the dimension of Rn is n. 5. What's another way of saying the dimension of the column space? That says that the rank of A is equal to n. 6. Well, if the rank of A is n, what does that mean about the nullity of n? Or the nullity of A. Remember, the nullity is the dimension of the null space of A. Well, let's think. I know that I have n columns, and I know that the rank of A plus the dimension of the null space of A has to be equal to n, right? Well, if we're invertible, I know that the rank of A is n, and I know that whenever I add the dimension of the null space, I have to be n. So what must the dimension of the null space be? The dimension of the null space has to be 0. Yeah. And what do we know about subspaces whose dimension is 0? So this is at the very beginning of this video. If the dimension is 0, what does that mean? That means that the null space itself is just the 0 vector. Yeah? And this is totally consistent with our previous idea. If we have an invertible matrix, yeah, then that means that we must have linearly independent columns. So what do we know about the number of solutions such that AX is equal to 0? There's only one, and it's the trivial solution, right? So this idea is totally consistent with our loop that we did in our previous discussion of the invertible matrix theorem. Cool. Let's talk about a theorem. Let H be a subspace of Rn. And suppose this thing has dimension equal to p, some number p, yeah? Then we know that any linearly independent set of p vectors is a basis. And any set of p vectors that spans H must also be a basis. Yeah? So if the dimension is given by p, and you have a linearly independent set of p vectors, then they must necessarily span the subspace. They must necessarily span the subspace. And if you have a set of p-vectors that spans, that set of p-vectors must necessarily also be linearly independent and thus therefore need to be a basis. Yeah? So our intuition here is that a basis is of a subspace, a basis of a subspace is a maximal set that is linearly independent. And a basis is a minimal spanning set. Yeah? So it's a maximal linearly independent set, and it's a minimal set that also spans the space. And remember, this kind of jives with our notion of how with our structure of what matrices look like, right? If we have a matrix and the columns span Rn, then our intuition is that we have a long, skinny matrix, right? If we have a matrix whose columns are linearly independent, our intuition tells us that it's probably tall and skinny, right? So a basis is kind of the best of both of these worlds. And what matrix is equally long and skinny and tall and skinny? Those are square matrices, right? Cool. And that's how it kind of goes back to the invertible matrix theorem as well. All right, so I hope that this helps. If you have any questions, feel free to reach out via email. I'm going to post some fun homework. I'm happy to also set up a time to Zoom and discuss any problems that you have. And I look forward to seeing you in the next video. Thanks so much for watching.